All right. Hey, everybody. Thanks for coming. Welcome. What a lovely way to end the week. Lovely to see so many people here. My name's Ben McAllister. I'm a scientist. I'm one of the researchers here at Swinburne in the Center for Astrophysics and Supercomputing. I'm going to be talking about dark matter, one of the biggest mysteries in the universe. Specifically, what we're doing here in Australia to try and shine a light on dark matter. So I'll talk a little bit more about these various symbols on the screen in a moment. But before we get to that, just like to begin by acknowledging the traditional owners of the land on which we're gathered, pay respects to elders past and present. It's really important to acknowledge that Indigenous Australians were the first astronomers. They had a lot of very detailed scientific observations of the sky. So very cool that that was going on so long ago. And we all follow on in that same tradition. All right, so who am I? As I said, I am Ben McAllister. I'm a scientist. I'm a member of two nationwide research collaborations. They're these things called Australian Research Council Centres of Excellence, which is just sort of like fancy research speak for government funding that is nationwide in sort of strategic specific areas. And they're usually collaborations of many universities, including Swinburne, where we are right now. So one of these centres, and the one that's most relevant today on the slide, is the Centre of Excellence for Dark Matter Particle Physics. So you might not be aware, in 2020, the Australian government invested $35 million over 7 years in dark matter research in Australia. So trying to answer this really, really big fundamental question that we're going to talk about tonight. What is dark matter? So that's what we're doing there. It's about a half dozen universities: Swinburne, University of Melbourne, University of Sydney, ANU, Adelaide, University of Western Australia, working together with international partners, all on different kinds of experiments, including some that we're going to talk about today. The other research centre I'm a part of is the Centre for Engineered Quantum Systems. So I'm not going to talk about that so much today. It's more about building new kinds of technology. And that's also a centre funded by the government. It's many universities, again, around the country. So we're working on like new kinds of technology, machines, devices for the future. And there's a lot of overlap between this work because it turns out when you're doing very, very precise physics, looking for new physics, trying to answer really deep questions about the universe, it can be really helpful to have brand new sensing technologies, quantum technologies, things like quantum computers and things like that. Okay, but with all that out of the way, we're here to talk about dark matter. This is a picture of some dark matter, believe it or not. It's actually none of the stuff you can see. It's a bunch of stuff you can't see. That's just a silly little joke. This is a thing called the bullet cluster. It's a picture that physicists like to throw up when they're talking about dark matter, because as we're going to discuss, dark matter is a thing you can't see at all. So if you want to show something, you want to show something that looks kind of cool. And the bullet cluster is one of the biggest pieces of observational evidence we have that tells us about dark matter. Looking at all this stuff we can see, all these clouds of gas and dust, we can extract a bunch of information about what's there, including dark matter. So we're going to come back to that a bit later. Dark matter, though, maybe you've heard of it, maybe you haven't. Let's talk about it. What are we talking about with this dark matter problem? So the dark matter refers to something that is huge. There's an enormous, enormous, enormous amount of this stuff throughout the universe. It's also everywhere, including here on Earth. In fact, as we sit here, it's passing right through you right now. There's an enormous amount of invisible stuff moving through this room, through our bodies, through the floor, through the planet, just passing right on by. We can't see it, touch it, or feel it, and we have almost no idea what it is. It is a huge cosmic mystery. To give you a bit of a sense of the scale of the mystery, we know that the vast majority of the universe is made of stuff that we don't understand yet. If we were going to put together a pie chart, it would look something like that. That little tiny sliver of blue there is the regular matter. That's all the stuff we understand. That big green chunk is the dark matter. That's the thing we're mostly going to talk about today. The stuff that we're trying to find in this research center I mentioned before. And then all that gray stuff is this stuff called dark energy, which we know even less about. We can talk about that after if you're interested. It's a huge, huge mystery as well. But we're talking about dark matter today. I find it's helpful when talking about dark matter, before we talk about dark matter and what it is or what it might be, it's often helpful to talk about what dark matter isn't. Because people think like, oh, okay, dark matter is that black holes. Fair enough, reasonable thing to think. But let's just define a few things. So I mentioned that like 5% of the universe is made of this stuff called regular matter. What is regular matter? Regular matter is what we refer to as all of the stuff that makes up people and planets and stars and black holes and galaxies and everything that we can observe. Basically, when we look in space with telescopes, everything we see, when we look around us on Earth in our day-to-day experience, everything we see is made out of regular matter. And we know now, thanks to several hundred years of particle physics, getting better and better microscopes and then particle accelerators and doing all kinds of experiments to look at the universe on very, very small scales, we now know that all of that stuff, people, planets, stars, galaxies, black holes, is really at its fundamental level made up of just a handful of different things. There's this thing called the Standard Model of Particle Physics. It's about 16, 17 particles that make up everything in the universe that we can observe in the regular matter. Everything we understand is different combinations of these things. Actually, we can take it a bit further. The vast majority of it is actually just made of these three things here. Different combinations of those three things make up all of the atoms in your body, and the Earth, and the Sun, and the giant supermassive black hole at the center of our galaxy is predominantly composed of this stuff as well. The other stuff is this like exotic stuff that plays other roles in the universe. But yeah, like most of that stuff is made up of these three things, and with an understanding of that regular matter, we can tell the story of the universe from the Big Bang. And it was a really, really hot, dense period where all the matter was very close together, and then it started to spread out and clump up from smaller particles into bigger things like protons and neutrons that make up the interiors of atoms, and then those clump together into atoms, and then hundreds of millions of years later, those clump together and create the first stars, which explode and spray all kinds of more exotic stuff around the universe. And you do that a bunch of times, and then you start making galaxies and planets and people and all kinds of cool stuff. And that is the story of the regular matter, which I hope you will agree is a pretty cool story. You start with all this tiny little stuff, and about 13 billion years later, you've got human beings who can look at it with telescopes and think about it. That's pretty neat. Well, we know now that that is actually only a small part of the whole story. There is, in addition to that stuff, the stuff that we just told that entire 13 billion year story of in 15 seconds, there is 5 times as much dark matter. In addition to all of that, galaxies, black holes, 5 times as much again, and it's been there the whole time, influencing this stuff, shaping it, shaping the way the universe develops, shaping the way galaxies form. I just want to highlight quickly that the name, dark matter, is actually a very, very descriptive name. It's a very good name. It's the best kind of name, because it sort of tells you everything we know about dark matter. It's dark, which means we can't see it. It doesn't interact with light, so we can't look at it with regular telescopes. And it's matter, which means it has mass to it. So it's heavy. It's not just some other kind of energy. It's something that's massive. So you might be asking the very fair and reasonable question, how do we know about this stuff if we can't see it or touch it or feel it? How do you know where it is? How do you know it's passing through the Earth? How can you know any of this at all? Well, the short answer is a couple of different ways, mostly thanks to astronomy, which is to say looking at space with telescopes at the way stuff moves around. So building big telescopes like those that are in the Australian outback or in South America. They can be optical telescopes, radio telescopes, the kind of work that Swinburne is very heavily involved in. So looking at distant galaxies, nearby galaxies, and just trying to understand the dynamics of the stuff in space. And it turns out when you do that on all kinds of different length scales, from individual galaxies up to very, very large clusters of many galaxies to the huge scale structure of the universe, on all of those scales, you have different pieces of evidence for dark matter. I've listed them there. I'm not going to go through them all. I am just going to highlight one of them, which is this thing called galactic rotation curves. So that is an example of a galactic rotation curve. I'll talk about what it is. So if you look at a galaxy like the Milky Way galaxy, the one we live in, there's a representation of a similar galaxy on the bottom of that image there. It's spinning. It's a spinning disk of material, spirally arms that spin around the center. So you could look at a galaxy like that with a telescope, and you could make measurements of how fast it was spinning as a function of the distance from the center. And that's what these graph axes represent. So the y-axis there, the up and down axis on the left, is how fast different parts of the galaxy are rotating around the center. And then the x-axis there, horizontal on the bottom, is how far we are from the center of the galaxy. So just looking at the way they spin and measuring velocities. If you just looked at that galaxy with a telescope, most of the stuff we can see is kind of all clumped up near the middle, right? That's where it's brightest. So there's heaps of stars and gas and dust there. So there's lots and lots of stuff near the middle of the galaxy that we can see. And that tells us that gravity should be strongest near the center of the galaxy. Because gravity is dependent on mass, heavy things have lots and lots of gravity, light diffuse things have very little gravity. So most of the gravity from the stuff we can see should be near the middle of the galaxy, which means the stuff near the middle of the galaxy can spin around really, really, really fast. It's like if you've ever spun a ball around on a string, you can only spin it so fast before the string breaks and the ball flies off, because there needs to be some force holding the ball moving in the circle. In the context of the galaxy, it's the gravity from all the stuff in the galaxy that holds everything together. So it's spinning around, gravity is really strong near the middle, so it's held together really tightly, so it should be able to spin around really quickly. Then when you get to the outer parts of the galaxy, there's not much stuff, it's pretty wispy, it's low density, at least in terms of things we can see. So gravity should be weak, so the stuff shouldn't be able to spin as fast without being flung off into space. And that's what that gray dashed curve there represents. That's saying like that's how we'd expect the galaxy to spin. Stuff near the middle spins fast, stuff on the outside spins a lot slower. That's just based on visible observations. But as this graph gives away, when you actually do these measurements in our galaxy and just about every other galaxy we've ever looked at, the curve looks more like that solid curve with the data points there, which is to say the outer parts of the galaxy in particular are spinning way, way, way faster than we expect. If all the gravity that was holding the galaxy together was coming from the stuff we can see, we'd expect those outer parts of the galaxy to be flung off into space. Galaxies would just be torn apart by how fast they were rotating. There's a little animation here that represents that quite nicely when it wants to load. Hey, there you go. So on the left there is how you would expect the galaxy to spin, again, just by looking at the stuff. So again, fast near the middle, slow on the outside. And on the right there is how they actually spin. So a bit of a mismatch. This has been understood for decades. Particularly a very clever scientist named Vera Rubin in the 1960s and 1970s did a lot of the famous work on this that is widely regarded as the most conclusive evidence for the existence of dark matter. So, okay, we've got some different observations that are saying, there's weird stuff going on, there's mismatches in how things travel around when you look at all the different scales of cosmology. So how do you account for that? What could it be? Well, there's two main theories you could have to explain all of those observations. The first one is you might say, well, what if gravity is just wrong? So all of this dark matter stuff is based on looking at the way things move around, so our understanding of gravity is very, very important. So maybe we're just wrong about the way gravity works in some really, really important way. And that's definitely possible. It's definitely a valid hypothesis, and it's a thing that people have been working on for a very long time. But for a number of reasons, it's not considered a very attractive or good hypothesis these days. Mostly because no one has yet been able to write down a theory of gravity that explains all the stuff that we see without breaking everything else. And that sort of is also connected to the other reason, which is like we know our theory of gravity has a few little problems in it, but it describes a lot of things really, 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 really precisely, like many, many decimal places of precision on the way planets move around in our solar system. So we don't want to junk that whole theory. It works really, really well. So no one's yet been able to make the we don't understand gravity thing work. So we're going to discard that idea for the moment and say, okay, let's assume gravity's good. Well, what if there's just some other stuff than this stuff? So I mentioned the regular matter before, made of these 16, 17 things. What if there's some other stuff in the universe? And why should that really be so surprising at all, that there would be extra stuff other than the stuff that we already know about? So maybe in addition to this standard model, there's another column called dark matter, where here there be dragons. There live some strange, interesting things that we don't understand yet. Maybe some things called WIMPs, which I'll talk about in a minute. Maybe some things called axions. Maybe some other more exotic stuff. All right, so if we wanted to have a new particle to understand dark matter, some new kind of thing, what would it look like? How could such a particle be? Who has heard of the 4 fundamental interactions of physics before? Okay, great, some of you. Those of you who haven't, don't worry. What these are the names of the 4 things we know so far the universe is allowed to do. And this is just like botany. We don't understand why there are 4. We don't really understand that well how they work. We just know we can sort of explain like everything we see in the universe in terms of some combination of these 4 things. So gravitation, we've been talking about a bit today. Gravitation is one of the allowed interactions in the universe. Something that has mass, something else that has mass, they are attracted to each other through this thing called gravitation. Electromagnetism is actually the main force that we experience in our day-to-day lives. If I push down on this lectern here, the reason that my hand doesn't go through it is because the molecules in my finger and the molecules in the lectern are holding tight to each other electromagnetically and repelling each other. So when you're standing on the ground, the reason you don't fall through it is because you're being supported by the electromagnetic interaction of the particles in your body and the particles in the earth. It's also the way magnets work if you bring 2 magnets close together. So that's a force that we have a lot of intuition for. The weak and strong interactions are a little bit more arcane. I'm not going to go into them in much detail. Suffice to say, they just have to do with the interiors of atoms. So very, very small scale things like they hold atoms together. So they occur on very small length scales. And when we look at everything we know about dark matter, we can infer the following things about any new dark matter particle. It must experience gravitation. That's the only way we know this stuff exists. It's pulling on stuff we can see, so therefore must have gravity. We know it can't experience electromagnetism for 2 reasons. One, it passes right on through. And remember what I said about pushing down on the lectern? If it experienced the electromagnetic interaction, it wouldn't pass through, it would bounce into stuff all the time. So it couldn't just be passing on through the Earth and all the other stuff in space we see it passing through. It's a bit of a subtlety here, but it's actually also because we can't see it, we know it doesn't experience electromagnetism. And that's just one of the weird things about particle physics. It turns out stuff that interacts with light, stuff you can see, must experience the electromagnetic force. Charged particles and things like that are the only kinds of particles that interact with light. So can't see it, can't touch it, no electromagnetism. The other 2 interactions, we know it can't experience the strong interaction, just because if it did, it would have blown up all of the atomic nuclei that make up our bodies and the rest of the planet and stuff. It would have, as it passes through, it would have just blown things apart, so it can't experience that. The weak interaction, maybe, which is where we get to the 2 candidate classes of dark matter. These things called WIMPs, weakly interacting massive particles, and these things called WISPs, weakly interacting sub-eV particles. Yes, I'm aware those names are kind of funny. That's just an important part of being a physicist. If you're going to come up with something, it has to have a dumb acronym. Often you come up with the acronym first, and then you try and make it fit later. So these names are names of particles that do what they say on the tin. They are particles that interact very weakly with the regular matter, and they're either massive, meaning they're really heavy, or they're sub-eV, which just means they're really light. So they're new kinds of particles that fit into these 2 broad categories. Okay, so we have understood that the universe is absolutely chockers with dark matter. There's tons of it, it's passing through us right now, and that it's probably made of some new particles that might be these things here. We've got a lot of indirect evidence for dark matter from, again, looking at the universe on all kinds of length scales. Indirect evidence. How would we come up with direct evidence for dark matter, which nobody has done yet? You might try and do what's called a direct detection experiment. So doing some kind of experiment to directly observe the dark matter through some other way than gravitation. Important to remember, when building one of these experiments, dark matter is all around us. It's actually passing through us. So we don't need to go to deep space to build these kinds of detectors. We can actually do it right here on Earth. And detect the dark matter as it comes to us. It just passes right on through. That's very convenient of it. The general hope is that the dark matter might interact weakly, so just some very small interaction, with some of the regular matter particles that make up our detector, whatever the detector is, and impart a little bit of energy that we can then observe. So we're essentially trying to take something we can't see, something that's invisible and unknown and secret, and get it to interact with something that we understand well. So we can get a little bit of energy in our system that we can then try and detect. Okay, let's talk about what these experiments look like. Okay, so WIMPs, I mentioned these before. They are one of the two major candidates for dark matter, and it is expected that they can interact with the nucleus of an atom. So if you look at an atom, like one that makes up your body, or the table or whatever, on a subatomic scale or on an atomic scale, that's what it looks like. There's this thing called the nucleus, which is the heavy bit in the middle, and the idea here is that the WIMP might come in, bounce off the nucleus, give it a little bit of energy. The nucleus of the regular matter recoils. This is like a rare event. This is like an interaction between the dark matter and the regular matter. And then when that nucleus recoils, you've given it a little bit of energy, and you can try and detect that in various different ways. There are a bunch of detectors around the world that try to exploit this effect of WIMP nuclear recoils. There are some of the names of them. I will highlight specifically the SABRE experiment, which some of you may have heard of. It's actually currently being built here in regional Victoria, in Stawell, about 3 hours drive away, in an abandoned a still functional gold mine. They are building one of these particle detectors. I'll come back to that in a second. No detections so far from these various experiments, which is sad, but also not all that surprising, given it took us 100 years to find gravitational waves and many, many hundreds of years to split an atom apart. Physics happens on slow time scales. You've got to spend a lot of time looking before you discover something. But the important thing about this is that when you don't detect something, you don't just go, okay, forget about that. What you do is you generate a thing called an exclusion limit, which is represented by this plot here. I'm just going to blow up one of them for the sake of vision. These things are called exclusion plots. They're very, very important in dark matter. So one of the things that makes dark matter detection very difficult is that we don't know the mass of the particle we're looking for. It could be really, really, really heavy, or it could be really, really light. We also don't know what the probability of it interacting with the regular matter is. It could happen a fair bit, or it could happen not very much at all. So you can build what's called a parameter space, that's what we look at here, where you've got the mass on the bottom axis there, horizontal, from very light stuff on the left to heavy stuff on the right, and what you can think of as like the probability of an interaction. So if it interacts a lot, it's somewhere up near the top. If it doesn't interact, it's down near the bottom. And the dark matter can live anywhere in there. It's just like a big parameter space. The dark matter can be anywhere. And when you build one of these detectors and you don't see anything, what you can say is, okay, no dark matter here. And then that means someone else doesn't need to look there again later. So this plot is a representation of various experimental limits that have done that. All of those lines and bands are essentially different experiments that look at different regions of the parameter space and say, okay, no dark matter here. And so physicists around the world are collaborating, carving out different chunks of this parameter space. Because when you build one of these detectors, you're only sensitive to some small chunk of it at any given time. So you look in some region, you say no dark matter here, and then the next generation of experiments don't look there again. That's an important concept. So SABRE, I mentioned before, is one of these experiments that is carving out a chunk of that parameter space. It's being built again here in Stawell in Victoria, which is very exciting. It's a giant tank of sodium iodide crystals. So just very, very, very pure crystals of something that's quite similar to table salt. Some of the purest crystals in the world are being built for this experiment. It is currently being built in a gold mine, as I mentioned, kilometers underground to shield from signals from deep space. So the important noise background in these experiments is actually cosmic rays. So just like high energy particles bombarding the Earth from space that we're all being struck with a couple of times a year. They would completely blow out detections in this thing. So they have to go deep underground. The rock protects from the cosmic rays. There's a little close-up of the detector. This is just a mock-up of it because, as I mentioned, it's being built. It's a big tank. Those little copper things there contain the sodium iodide crystals. The hope is that the WIMP particles come in, they bounce off some of the nuclei of the atoms inside the sodium iodide, and then they recoil, they jiggle around, they have some extra energy. They lose that energy by spraying out little flashes of light, which then those camera bulbs around the outside will detect. So that's the idea behind SABRE. It's being built in the Stawell Underground Physics Lab, the first underground physics laboratory in the Southern Hemisphere. Very, very exciting. As I mentioned, construction is underway right now. Experiments expected to run sometime next year. All right. That is WIMP detection, specifically SABRE. I'd like to talk about the kind of dark matter that I work much more on myself. I do a little bit of work on SABRE. I mostly work on a different dark matter candidate, a much, much lighter particle called an axion, which I'm sure you've all heard of and probably learned about in primary school. An axion is a hypothetical particle having no charge, zero spin, and some small mass postulated in some forms of quantum chromodynamics. Everyone's with me, presumably? Okay, well, If you're not, don't worry. All you need to know about axions is that they are a really good dark matter candidate. And you can take my word on that, or you can come talk to me about it later if you're interested. Axion, as a name, again, silly names, very important. Actually named after a brand of dish soap, not a joke. There was a guy, his name's Frank Wilczek. When he was a PhD student, he always said, if I ever discover a particle, I'm naming it after Axion brand dish soap. And then he proposed the existence of this particle. It cleans up lots of problems in physics, and he said, great, there you go, axions. So that's what I spend my time looking for. All right, axions, what about them? They're much, much, much lighter than WIMPs. That's the main thing that distinguishes them. So WIMP particles are about the same size as an atom, about as heavy as like one of the atoms that makes up your body. Axions are many billions of times lighter. So they'd be much, 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 much lighter than even an electron, for those of you who know what that is. They're motivated by a different area of physics to WIMPs. I'm not going to go into the details. Again, talk to me if you're interested about that. The neat thing about axions is that they can interact with what are called photons, which are particles of light. So all the light coming out of these, the light that hits Earth from the sun, all the light that you've ever seen is actually, on a small scale, made up of these tiny little things called photons. They're particles of light. And it's great that we can have an interaction between axions and photons, because photons are the thing that, as a species, we are the best at detecting. So that's great news. We can exploit this thing here. This is a real physics diagram. It's a thing called a Feynman diagram that represents the interaction of axions and photons. The squiggly lines are photons. The dashed line is an axion. So the idea of this coupling is an axion comes in from dark matter, from outer space, and it interacts with one photon, one of these squiggly lines that we provide in our experiment, a little bit of light, and then out comes another photon, a little flash of light. So we're essentially generating the right conditions to stimulate what's called axion-photon conversion, effectively taking something invisible, dark matter, that we can't see or touch, and turning it into a little flash of light, which again is the thing we're best at detecting. So that is great news if you want to build an experiment. How do you build one of these experiments? You make a thing called an axion haloscope, where we generate the right conditions to stimulate axion-photon conversion and then try and detect that little photon signal, that little light flash. Here's a little cartoon. You've got some mysterious thing, some dark matter. You've got some detector. You'll see why it's shaped that way in a minute. The dark matter comes in and boom, converts into a little flash of light that you can try and detect. So what are the things you need to have an axion haloscope? You need it to be really, really, really cold. You need something called a resonant cavity. And you need it to be submerged in a very strong magnetic field. So let's talk about each of those things. Why do you want it to be very cold? Well, we're looking for very small flashes of light, very small light signals. And everything that has any temperature is constantly emitting little signals of light. If you've ever looked through a thermal camera, like this one, then you know that for yourself. Infrared imaging is the result of exactly this. So anything that is warm is just constantly spraying out little signals of light that would completely destroy our ability to see these tiny signals of light from dark matter. So we make things really, really, really cold, reduce the amount of background noise kicking around, and have a better chance of observing the dark matter. What's a resonant cavity? Who's ever played a flute or a recorder or some kind of woodwind instrument? Okay, a couple of people, that's great. You'll know that if you blow into a cylinder, there are certain frequencies of air vibration that will resonate, that will make a really, really loud noise. And even if you stop blowing, for a short amount of time, that noise will keep ringing. That's called a resonant cavity. Or if you've ever had like a drink bottle and like blown in the top of it, if you hit the right pitch, it'll kind of resonate inside there. Turns out that's not just true for sound waves, it's also true for electromagnetic radiation, or photons, or light. So you can make a thing called a resonant cavity. It's a cylindrical shell of metal, and there will be certain frequencies of electromagnetic radiation that bounce around inside. They ring up in the same way as blowing into a flute or a recorder or something like that. So we're trying to detect little light signals. Having them get trapped and bounce around inside our resonant cavity makes it a lot easier. Here's what one of these things actually looks like, by the way. It's about yay big. This is actually an axion detector. It's that little copper cylinder at the bottom there. So the idea is there are certain frequencies of light that get trapped in there and bounce around. And the magnet is just the way we stimulate axion-photon conversion. So the magnet supplies one of the two photons in our interaction. It's just it's an important thing that you need to make axions decide to convert from something we can't see into a little flash of light. So it's a very, very important part of the experiment. Similar to WIMPs, there is a large parameter space to search for axions. This is what it looks like. Mass on the horizontal axis, heavy axions on the right, light axions on the left, how likely it is to convert into a little flash of light on the side axis there. So likely at the top, not likely at the bottom. And again, different experiments rule out different regions of this parameter space. So all these different color bars and stuff are different regions that experiments have looked. If you look at this graph for a moment, you'll notice there's a lot of experiments there, and there's a lot of empty space out here. And there are good reasons for that. And that is because it's comparatively easy to build experiments here and quite hard to build them out here. And that is what we're trying to do here in Australia with our new cutting-edge dark matter experiments. Look in these regions of the axion parameter space where no one else is looking. Why is it hard to do that? This is the only equation I'm going to have in my talk. I know it's gross, don't worry, it'll be gone in a minute. All this equation tells you is that the frequency of the light that's generated, that's that little omega symbol there, that W-looking thing, depends on the mass of the axion. That's ma there. So what that means is when the mass is high, so when we're further to the right on that plot a moment ago, the light frequency is really, really high. And when that mass is low, when we're further to the left, the light frequency is really, really low, the electromagnetic radiation frequency. So don't worry about that, just the frequency depends on the mass you're looking for. And then if we think back on our resonators, our resonant cavities, who has ever, when blowing into a bottle of water or something, when you hear that resonance, if you add more water to the bottle, does the resonant frequency go up or down? Does it go up or down in pitch as you fill the bottle up more? Up, right. So you're making the resonant chamber, the air pocket, smaller, and the resonant frequencies go up. If you make the air pocket bigger, the resonant frequencies go down. The same is true for electromagnetic resonators. So if we want to catch high frequency radiation, our resonators get very, very, very small. And if we want to catch low frequency radiation, our resonators get very, 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 very big. And both of these present challenges for experiments. Here's just an example there. Those are like the wavelengths of the waves that bounce around. If you make the thing big, you stretch it out, low frequencies. If you make it small, you compress it. Anyway, what that means is that this region here is where it's comparatively easy to build experiments because the resonators are of a reasonable size. Out here, they get too small. And that means that there's less dark matter inside your detector because it's tiny, which just means that your chances of observing it go down. So it's just harder to do. And out here, you have a different problem, which is that the detectors get huge, the resonators are enormous, and that means that you can't fit them inside the magnet anymore. The magnet being the really, really important component that makes the experiment work. It's the thing that makes the dark matter turn into little flashes of light. And the magnets are just limited in physical size. So if you have a big, big resonator, you're in trouble. You could say, too big, too small, just right. And that's why everyone does their thing there. But again, that is where we come in here in Australia with what we call the Oscillating Resonant Group Axion Experiment, or the organ experiment. Again, acronym first, worry about what it means later. We're definitely part of the same club. So organ is the Dark Matter Center, again, this nationwide collaboration of universities. It's the axion haloscope that center works on. It is mostly hosted at the University of Western Australia. Here is a picture of the experiment. We contribute to it from here by designing some of the parts that go into it. That little copper can that I showed you before, that is the detector. All of that gold stuff around it, that's the refrigerator. The only purpose that serves is to make the whole thing very, very, very cold, for the reasons I outlined before. It's actually an extremely cool piece of kit. That is a pun, but it wasn't meant to be. It's very, very, very cold. It gets down to what's 7 millikelvin, so 0.007 degrees above absolute zero, or something that's like negative 273-ish degrees Celsius. So very cold. And as I mentioned, if we want to go to high mass axions, that's high frequency. That means that the cavities get very, very small. So that is why that detector is quite small. But, as I mentioned, there is a brand new axion haloscope detector being built here at Swinburne right now. Here in Victoria, our very own experiment to explore the low mass range, the region on the other side of where most of the current experiments are. So, we're calling it the organ low mass or organ low experiment, being built here, currently being developed. It's big. for the reasons I outlined before. So yeah, it's a little over 1 meter long. Those dimensions are in millimeters, so you know, big. And it's about 600 mil around, so I guess something like that, roughly person-sized, which presents a problem if you want to do dark matter detection, because where are you going to get the magnet for that? Where's it going to go? Well, we've got an MRI magnet here. We're actually sitting on top of it right now, and it fits things that are roughly person-sized. So the Swinburne 3 Tesla MRI magnet, pictured here, is currently being repurposed partially for a particle physics experiment. We're very, very excited about that. It's a collaboration between health sciences and particle physics, doing some cutting-edge science with stuff we already had kicking around. Again, that detector well, the MRI magnet is actually just like pretty much directly underneath us right now. It does get used for some medical imaging and medical imaging research, but mostly, well, it's research focused, and we're using it for dark matter. So that is a bit about our plan to push into those two regions, the high mass axion region and the low mass axion region. That's what we're doing here in Australia. But if this parameter space stuff is a bit arcane to you, don't think about it as a parameter space. Don't worry about the physics. You can instead think about it as a map. You could think of it as a map of all the places the dark matter could be. And all these different color bars here are just different people going, we've already looked here, we've staked our territory, and we haven't seen any dark matter. And the big scramble in the field at the moment is to get into those white regions, the region where nobody has done these experiments before, because that is where new physics is hiding. That's where the dark matter could lie. And as far as we're concerned, with Australian dark matter detection efforts, X marks the spot. These are the regions we're interested in building detectors. So I just wanted to talk a little bit before I wrap up here about why we care about doing this. Why did the government give you $35 million? Why should we do this at all, right? I'm imagining, given you've chosen to come to an astronomy thing on a Friday night, that you're probably kind of down with it, and that's great. But it's still worth talking about. It's a worthwhile question. I think there are a couple of different kinds of answers you can give to that question. The first kind of answer is kind of like practical. We just know from history of science and history of research that doing this kind of research, we generate all kinds of technologies that spin out of them. We know the space race didn't just make spaceships. Unfortunately, a lot of that is tied to history of war and stuff. So the neat thing here is that it's not, it's just physics research, but we end up making all kinds of new technologies that have all kinds of incredible applications just by doing fundamental research. But you can take that a step further. Doing fundamental research like this, fundamental physics, with no specific understanding of what exactly is going to come out of it, is the only way we ever discover anything new. It's not like someone sat down one day and said, I'm going to start making a thing that will one day be a very small component of an iPhone. They were just looking at interesting physics, things they didn't understand. Why does this rock feel weird when I put it next to this rock? No idea what that's about, play around with that for a while. Oh, I just discovered electricity and magnetism. So you've really got to ask those fundamental questions without knowing what's going to fall out. You can never discover anything new by only asking questions you already know the answer to. I mean, doing that kind of incremental research where you know very defined what's coming out is very, very important. That's the stuff that's going to save the world in the short term. Like, oh, I want to improve the efficiency of these solar panels by 3%. That's incredible research and needs to be done. But at the same time, you have to do the fundamental research or you will never discover anything new. Great example of this, the discovery of radio waves, which currently underpin all communication technology, among other things. Discovered in the early 1900s by a person named Heinrich Hertz. At the time, when they were discovered, a reporter famously asked Heinrich Hertz, why did you bother? You generated radio waves over here in your lab and you detected them over here. What possible application is there for doing this? And he was like, I don't know, probably nothing. It just seemed kind of interesting. And then, of course, that is the entire modern world. So, I mean, that's just an example of why doing this kind of stuff is important. And to put it another way, I like to say, take a look around at everything that humans have accomplished as a species. Computers, modern medicine, space travel, all of art and literature, and understand that we've done that with an understanding of just 1/6 of the matter in the universe, and then imagine what we could do if we could unlock the rest. There's so much stuff out there that we're yet to understand. With that, I'll leave you with some places you can go looking for more information, and have some time for questions. So thank you. Sure, yeah. You. Thanks, Lisa. Lisa will bring the mic around.
Thank you. I just want to question about the detection of the photons. Are you using some special detector like a photomultiplier, or are you using more solid state detectors, and are they a limitation into your ultimates detection range, if you like?
Yeah, fantastic question. The answer is different depending on what mass range you're looking in, because as it sounds like you probably know, photon detectors are bandwidth limited. So you can have a photomultiplier, for example, that works really, really well for optical frequency photons, so very, very high frequency. When I threw up this picture of SABRE before, the WIMP detector, that's actually what those little bulbs are around the outside. They are photomultiplier tubes. So when doing like a SABRE experiment, you do use those. When you do axion stuff, the photon frequencies are much lower, so you wouldn't use photomultiplier tubes. They're in the sort of similar to telecom band, so we use like solid state components, things like microwave amplifiers and things like that. And yes, they're a huge limitation. They're one of the biggest limitations in the experiment, is how sensitive those light receivers can be. And that's where the engineered quantum systems work comes in, because building next generation light sensors is quantum technology. The smallest number of photons you can detect is 1. If you find a way to detect 1 photon, that's a quantum sensor that you've just built. So that is where that work overlaps. Hopefully that answers your question. Great. Sorry, and this gentleman?
Yep,
I think you've...
a far less question, a far less technical.
Yeah, right, great.
How are we seeing that dark matter?
Yeah, great question. So mic cut off for anyone who didn't hear. The gentleman has asked me, I said we use this bullet cluster because it's a thing that relates to dark matter that you can actually see. Right, so the bullet cluster, what we're seeing here is actually the collision of multiple galaxies, or the collision of 2 galaxies. And what astronomers are able to do is look at where all the stuff they can see is. Obviously there's clouds of gas and dust and stuff. And then look at where all the matter is by using this thing called strong lensing. So very high regions of mass density in space bend light around them. So if you've got a really, really dense pocket of matter in space, and then there's a star on the other side of it, the light from that star gets bent around it. And if you're here on Earth and you look that way and you look that way, you see the same image of the star that's on the far side of the heavy thing. That's called strong lensing. So you can look at a picture like this and do very complex calculations to say, okay, based on the lensing that I can see in this image of just the distant background of stars, where's all the mass? Where's all the heavy stuff? And they see that all the heavy stuff is not in the same place as all the stuff they can see. All the heavy stuff is further out, and all the stuff they can see is in the middle. And what they were able to reconstruct is that when these galaxies collided, all the stuff they can see smashed into each other, and it was chaotic and jets spraying everywhere and kind of clumped, and all the dark matter just went straight through, because it doesn't interact very much at all. It doesn't interact with the regular matter, it doesn't experience electromagnetism. So it was a couple of pieces of observational evidence. Cheers.
What is the red and what is the blue?
Those are just different frequencies of light that the cameras have observed. Different particles and stuff, different molecules emit different frequencies as characteristic signals. You wouldn't actually see this with one image, by the way. You'd take 3 or 4 different images using different filters to get different light frequencies, and then you superimpose them later.
Which other countries are doing this research apart from Australia?
Right. All the big ones. The US is a major player in this space. US research into dark matter is largely funded by the Department of Energy, which is kind of interesting. You might wonder why it's funded by the Department of Energy, and it's because there are people who expect or believe that dark matter could be used as a huge free energy source. We've got heaps and heaps and heaps of mass. If you can find a way to dump that mass into energy, according to Mr. Einstein, E equals mc squared, you get lots and lots of energy out. Particularly with axions, this is promising because we're already converting them into little flashes of light, which is electromagnetic energy. That's an aside, but the US, South Korea has a big program in axion detection. More and more it's happening around Europe. And dark matter detectors, WIMP detectors, I'll call them older style dark matter detectors, are kind of everywhere. Everywhere there's a gold mine, someone's sticking one of these things. Yeah. Thanks.
Given we know so little about it, is it possible that dark matter existed pre the Big Bang, and even maybe was the gravity force or whatever it is that sparked the Big Bang?
Right. So these are the truly big questions where the answer has to be we just don't know. As far as we know, the current model of the Big Bang is that asking the question what happened before the Big Bang is like asking the question what's north of the North Pole. It's not that it's a silly question or that there's no answer. It's just that by definition nothing. So that there was no before the Big Bang because the Big Bang was the beginning of time. Much like there is no north of the North Pole because the North Pole is the northmost thing. So asking So the canonical answer would be no, because nothing existed before the Big Bang, because there is no before the Big Bang. But different models of dark matter come into existence at different points in the universe's history. Some of them are there from the very beginning, some of them freeze out later. So hopefully that's a bit of an answer to that question.
Thank you.
Where do neutrinos fit into this picture?
Yeah. Yes, great question. Neutrinos are sort of by definition a form of dark matter because they have a bit of mass and we can't see them and they're very weakly interacting. So yes, very astute question. Neutrinos are sort of dark matter. We just know they can't be all the dark matter that we see because they'd need to be like way, way, way too many neutrinos and then we'd see a lot more of them. So we kind of know what the neutrino flux is like through the Earth based on our neutrino detectors. And if the neutrinos accounted for the huge amount of dark matter, then we would see way more of them. So yeah, there are some for sure, and they do make up dark matter. Some people believe, so I mentioned there were other dark matter candidates in addition to WIMPs and axions. One of them is this thing called a sterile neutrino, which is a reasonably popular dark matter candidate that some people look for, new kinds of neutrinos.
There's been a recent paper, excuse me.
Hi. Thank you.
There's been a recent paper published suggesting that something called axial Higgs boson, which is the second boson, I don't believe it's verified yet, but it seems to tick many of the boxes as a candidate for dark matter. Are you aware of it?
Axial Higgs boson. I know that there are various like Higgs mechanism dark matter candidates. I haven't heard of that one particularly, but I'll look into it. That sounds interesting. Thank you.
If we can't see dark matter and we
Yes.
can't feel it,
Yes.
how do we experience it to know
Right.
that it exists?
Yeah, so that's the astronomy observations that I mentioned before. Things like this, like looking at the bullet cluster, and things like this, where we look at the way galaxies spin. So like we look at the short answer is we look at the stuff we can see and we look at the way it moves. And from looking at the way it moves, we can infer the presence of the dark matter. So it's like you can't see it, but you can see it pulling on other things. Like you can see regions of space where there's nothing you can see that stuff's being pulled towards. So that's the idea. In terms of like what impact it has on us right now, if it didn't exist, our galaxy wouldn't have formed, and we'd be flung off into space. If the sun was traveling at the speed that it is, and there was no dark matter, we'd be very far away from the galaxy. There would be no galaxy, in fact. But yeah, thank you. Yep.
Hi, my question is pretty similar to that last one. You say it's passing through us.
Mm-hmm.
How do you know it's passing through us?
Right.
How do you know it's not just static and it's here and it's
Right.
but can't be detected?
Sure. So saying it's passing through us is actually a question of this thing called relativity. If I have this hand here and this hand here, you can pretty readily say, oh, this hand's moving towards this hand, right? But if you were this hand and you lived on the surface of this hand, you would say this hand's moving towards me. So it depends on what reference frame you're looking from. The dark matter, if we look on like a big kind of beyond our galaxy scale, is actually not moving very much. We are moving through it. So it's like a big blob that's just kind of, the galaxy just is in a lump, and it moves in random directions with an average velocity of 0. But we are bound gravitationally to the sun. So the sun, well, on this animation, the sun is one of those little bright dots in one of the outer spiral arms that's moving around the galaxy, and we're whizzing around the sun in a circle, and that's dragging us through this big blob of dark matter.
Oh, cool.
Yeah, then here. Yep.
Yeah, so if it was...
There's a little button on the front, just, yeah. Yeah, push to start, yeah. I'll repeat it.
If it was really strongly
Yep.
So do you think possibly the concept of mass is different for dark matter as to that it interacts with space-time in a different way?
Yeah, it's possible. It would be a fairly exotic model of dark matter. I mean, sort of the only, like, the indirect evidence we have for it at the moment is based on it just interacting the way mass does. So that's where the model comes from. But you can construct lots of more exotic models of dark matter based on different things. To go back to, I'll just jump back through, talking about these 4 fundamental interactions, speaking of interacting with gravitation in a slightly different way. I like to think of these things as like, again, they're just like stuff the universe is allowed to do, and whether a given particle interacts with them depends on what properties it has. Like if a particle has, like you can imagine it like an Excel spreadsheet and be like, okay, electron, proton, whatever, and then as you go down the columns, it's like, does it have charge, does it have mass, does it have spin, does it have whatever? And there's either a tick in the box or there's not, and that tells you whether it experiences any of these interactions. Dark matter, as far as we know, in the mass box, there's a big yep, and that's the only way we know about it. So you could imagine a more exotic thing that was like some kind of new particle that would interact in a different way, but then it wouldn't be gravitation. It'd be like a fifth force, which is one of the kinds of new physics people look for to try and explain these kinds of phenomena. So the answer is like, yeah, effectively you could have something like that. It would be a slightly different model of explaining these same observations, and people do look for that. Yeah, thanks.
With voids in between galaxy clusters, do they have anything to do with dark matter?
Yeah. Broadly speaking, the dark matter is where the matter is. The voids are pretty voidy. It would probably be more accurate to say that the regular matter is where the dark matter is, because there's a lot more dark matter. And the dark matter is like the seed, the gravitational seed that causes everything to clump up into these strings. So voids between galaxies, there's not expected to be much dark matter. The dark matter is pretty much where the stuff we can see is, if that makes sense. It's actually much bigger. It exists in this thing called the dark matter halo. Like if the galaxy's this big, the dark matter blob's like this big, because there's way, way more of it. Yep.
I was just wondering how large areas of the parameter space are filled out. I noticed there were some sort of areas there. One of them had to do with black holes. How can you sort of exclude looking in those areas?
Right. Okay, so like this thing here, you mean? Like which regions are plotted out? So you're asking about like the thing that says like cast at the top, for example? That like red bar? Or? And also the black hole one in the bottom left. Right. Sure. So those are like, so the black hole one is like astrophysical observations. That's to do with, like, if axions were that low mass and in that coupling band, then they would interact with the physics of black holes in such a way that black holes wouldn't spin the way we observe them to. So they would just like mess up the way black holes form. So you can derive a lot of limits from just looking at stuff in the universe and saying like, okay, another example of this, I'm not sure if they're on here, is like limits from supernovae. Yeah, so SN 1987A, for example, that thing there, and star clusters and various other ones that are up on there, is essentially saying like, okay, here's a thing we know, black holes behave this way, or there are supernovae that look like this. Let me plug axions into the physics of that thing and see what kind of axion parameters break it and make it stop working. And then the fact that the black hole behaves that way, or the fact that the supernova is that way, means the axions can't be there. Does that make sense? You just take like existing physics and yeah. And then, yeah, you can do all kinds of experiments as well, which is most of the rest of them. Down here.
Why is it that you can't see dark matter on the scale of the solar system, and yet you can see it on the scale of a galaxy?
Yeah, great question. It's to do with the fact that the solar system is very small relative to a huge galaxy-sized blob of dark matter, where the solar system sits within a pretty uniform sphere of dark matter. So as far as the solar system is concerned, there's as much dark matter on this side of it as there is on this side of it, as far as the sun is concerned in our little local area. So it's kind of pulling evenly in all directions, so you don't see anything. But when you're looking on like galaxy scale, in terms of its gravity with respect to the galactic center, it's further out in the blob, so there's more mass on the inside of it than there is on the outside of it, so you get like a net force pulling it inwards. Does that make sense? Like in our solar system, the Earth experiences like the same amount of dark matter in every direction, essentially. it's dominated by the mass of the sun, which is much, much closer and much, much denser, and then the dark matter just pulls on it a little bit. But the net effect of the dark matter on a galaxy scale makes a big difference to the way the sun orbits the center. Does that make sense? Cool. Yeah. I'll draw something for you later that might help.
Folks, thank you so much for your questions. Shall we thank Dr Ben?
Thank you.